Hi, pre-calc students. Welcome to your first lesson on factoring. We have a quick factoring unit to start the year here, and I think all the techniques that you're about to see you'll be pretty familiar with. So I'm going to turn on my camera here, and this should be on the first page of your factoring packet that you received from me. So if you want to kind of keep up with the notes as you go along, I will say moving forward, there are probably more days that you'll have to take notes by hand rather than having a note page in the packet, but just as kind of a quick heads up there. So the first thing we're going to take a look at really quickly here is reviewing the factoring technique called GCF, or greatest common factor. So the first thing you're going to want to do is look at all the terms in your polynomial here, in your expression, and determine what is the greatest common factor. So for something like this, you might want to look at the coefficients first, the 20, the 5, the 15, and hopefully you can quickly identify that the largest factor you can take from all three of those is 5. And then you would move on and do one variable at a time. So it seems like we can take at least one A, and then we can take at least one B from everything. And when I do that, what you're going to do is then think about dividing each of these terms by that GCF 5AB and think about what those leftovers are. So the first term would become 4A, and the second term would be a minus in the middle here. Let's see, it looks like I'm just going to be left with a B there. That's the only thing I think I would have left if I divide out the GCF of 5AB. And then at the very end, it's going to say plus 3. And as a quick reminder, factoring is really important throughout our entire course. But what I'll tell you is that you can easily check something like this by just doing a quick distributive property in your head, right? If you were to distribute 5AB back through, hopefully we're going to get 20A squared B minus 5AB squared plus 15AB. So that's looking good for number 1. Number 2, this is not as obvious that this is a GCF problem with these binomials, but that binomial x plus y happens to be the GCF. You may be familiar with a technique last year from Algebra 2 called dummy variable factoring or substitution. So I won't do this all the time, but if it helps you to visualize it, why don't you let A equal the quantity x plus y? And when I do that, this becomes AC minus AD. So now I think students more easily determine that, oh yeah, A is a GCF here. If I factor that out, I'm left with the quantity C minus D. The only thing I want to caution you about when using a dummy variable like this is don't forget to replace A with what it was equal to. And in this case, it's equal to the quantity X plus Y. So when I resubstitute that back in, now this is in factored form. By the way, for something to be in factored form, we want to express it as a product. So if you in the end think that you've completely factored something, but terms are separated with pluses and minuses, then we need to go a little bit further with that. All right, method 2, what we have here is the difference of perfect squares. This is something that I think we're super familiar with. The general pattern for x squared minus y squared would be x minus y and x plus y. And because multiplication is commutative, you can certainly switch the order here and have x plus y first and x minus y second. Moving on from there, a squared minus 9b squared, since these are both perfect squares, think about taking almost like the square root of those terms to figure out what the x value and the y value should be. So this would be a minus 3b and then a plus 3b. For number 3 and number 4, these might be good examples to consider that dummy variable technique we did up in number 2 over here. Notice how I use the variable a, by the way, up here. I didn't want to say let x equal x plus y. That gets really confusing. You know, down here you could say, hey, let x equal a minus b squared, or just the quantity a minus b, I should say. So let's do let x equal a minus b. And you get x squared minus 81 when you replace it. So factoring that would become x minus 9 and then x plus 9. So don't forget to replace a minus b back in for those x values. So the final factorization would be the quantity a minus b minus 9 and the quantity a minus b plus 9. You'll see that sometimes I'll write this answer with those parentheses there, and sometimes I'll sort of drop them, because in this case, the minus 9 and plus 9 after the quantity a minus b, the extra set of parentheses don't do anything necessarily extra for us that we need them there. Okay. Whereas in this case, this one would be a little bit tougher. You might want to try dummy variable on this one. So if you want to see how you do on number 4, maybe hit pause quick, see if you can get the correct factorization. I'm going to jump right into it without a dummy variable and say that this would factor into the quantity x plus y. And then you would have something like a minus the quantity a plus b, and then x plus y plus the quantity a plus b. One quick note about this answer that I just came up with here is that the parentheses in the second instance are actually more important than in the first, keeping those double parentheses on the inside. The reason being is that in this first factor, I'm subtracting a binomial. So if you wanted to drop the inner parentheses, you certainly could, but I'm just going to write down quickly here what that would look like. So let me just adjust the camera here for a second. The result, if you drop the inner parentheses, would be x plus y, distribute that negative, minus a minus b. And then for the second quantity, with that plus out front, that's not going to really affect the second binomial at all. So you would just have x plus y plus a plus b. I would accept either of these answers. If you like the way it looks without the double sets of parentheses, then that's just maybe personal preference on your part. But recognize that these are equivalent to one another. If you're going to drop those inner parentheses, make sure you distribute the negative where appropriate. Finally, in the last few cases, method 3 is trinomial. What we have for these is a trinomial is, I'm hoping you remember, a polynomial that has 3 terms. So if we go ahead and consider some factoring techniques here, if you look at something like number 1, we like when the lead coefficient of x squared is a 1, because we can use this technique that I think students have commonly referred to as the AM method, or the add multiply method. So you want to think of numbers that multiply to negative 15 but add to negative 2. And if you took a second to think about those possible factors of 15, you would pretty quickly come up with the factorization x minus 5 times x plus 3. Okay, moving on to something like number 2 here, 2x squared plus x minus 3. Students tend to not love this type of factoring as much because you can't necessarily just directly go to the AM method. There are a variety of techniques that students use to factor like something like this. I tend to just use a method called guess and check, where I set up my 2 binomials and I say, well, hey, the only things that multiply to 2x squared are 2x and x. And then the only things that multiply to negative 3 are some combination of 1 and 3. But where I place that 1 and 3 will matter because one of them is going to get multiplied by 2x. The other is going to get multiplied by 1x. So it's not as straightforward as thinking of it as we did in number 1. Some of you also kind of like what's called, I guess in my opinion, the reverse Fox method, where you say, okay, well, 2x and x are what multiply to give me 2x squared. And I know to get negative 3 in this bottom right corner, I have to figure out the 1 in the negative 3 piece. But what we have to remember is that these 2 terms right here have to give us a middle term of positive x. So wherever I place that positive and negative term that are associated with the 1 and 3 factors here, I have to make sure that this sum is a total of positive x. And if I think about that real quick for a second, it looks like if I do, to get positive x, how about plus 3 here and minus 1 here? Does that work? Let's see. So negative 1 times 2x would put negative 2x in this location. 3 times x is 3x in this spot. And those do combine to give you positive 1x. So now I'm confident that the factors are 2x plus 3 and x minus 1. And this one was kind of nice because these numbers are prime, so there's not a lot of options to consider. Sometimes if the numbers aren't prime, it takes a little bit longer, but just be a little bit patient with that type of factoring. For those of you that know something called slip, slide, divide, I wouldn't fault you for doing that. Where I would fault you is if you do it incorrectly. So if you have questions about that process, you'll let me know. Otherwise, try and just see if you can logically think about it using maybe a guess and check process. And this essentially is guess and check. It's just organizing it into that box pattern that you're probably familiar with from Algebra 2. Lastly, y to the 6 plus 2y cubed minus 35. If we go ahead and factor this, it looks a little scary when you have that y to the 6 term there, but it's going to factor pretty similarly to what we saw in number 1. You know, the things that multiply y to the 6th are going to have to be y cubed times y cubed, because the only term that I have in the middle there is y cubed. And you're going to apply that same AM rule, what multiplies to negative 35 but adds to 2. So when I do that here, you're going to get a plus 7 and a minus 5. And that's our really quick first lesson on factoring. So the next time I see you, we'll probably do a little bit of practice with each of these techniques, make sure that we have a really solid foundation of factoring with GCF, difference of perfect squares, and trinomials. and I really can't wait to jump into some more factoring techniques this school year. All right, we'll see you guys later.